Okay. Yeah, we started. So last time I didn't mention. I talked about the space of homomorphisms, how they're represented by matrices. Now let's give their dimension, and then I will proceed with the next topic. So I mean, because we can represent homomorphisms with matrices, they have the same dimension as the space of matrices, but let's write this down. So consider a commutative ring with unity. V and W are finite dimensional R modules. Then the dimension of the space of homomorphisms is equal to the dimension of V times dimension of W. Okay. And I will just sketch the proof. I mean, even last time I sketched how the construction is going on, I didn't prove its isomorphism and things like that, but I don't have them such small details. So consider two bases. So let's take ordered basis, because last time I was asked why sometimes I use square brackets for bases and why sometimes I use curly brackets. When I use square brackets, I mean the basis has some order. So let E be an ordered basis of V and F. Let's call this N and this M. F1 be an ordered basis of W. Then the following map. So we start with E to F. So it's an isomorphism from this space to the space of matrices M times N, I think. Yeah. Is an isomorphism. So if you remember last time, this is how when you have an abstract linear operator, but you know basis of the two vectors, two modules, you can form a matrix. And so I didn't talk about that, but it's logical that isomorphic things have the same dimension, because isomorphic things are in some sense the same. Then dimension of the right hand side, so hence, let's say hence dimension of equals to the dimension of And this is n times n. Dimensional space of matrices. But m is the number of elements in the basis of W, so this is dimension of W times dimension of V. And n is the dimension, so this is and this is n. Okay. Now let's start with dual spaces. This is a topic that for some reason is not covered in many introductory linear algebra courses, but we will need it very much. So dual spaces, because one of the most important spaces that the spaces of differential forms in the continuum and the spaces of cochains in the discrete world, they are all dual spaces. Sorry, not dual spaces, but dual modules maybe. They're dual spaces when we talk about vector spaces. Okay. So let's define them. So let R be an commutative ring with unity. V be an R module. The dual space yeah, it's space in the abstract mathematical way of space. I mean, everything is space in mathematics in some way. The dual module of V is V star, which by definition is the space of, maybe I should change. Okay, so this is the space of the linear functions from V to R. So this is the space of F from V to R. F is linear. For example, let's give some example. So this is a particular case of the whole home space, but let's give some concrete examples. So for instance, the dual space of R squared, any dimension will work, but let's fix R squared, is the space F of R2 to R. These are real numbers such that F is linear. And this is also the space of the following functions. So I haven't introduced that notation, but this is anonymous, some kind of lambda function used in programming, if you heard that. It's a function given by its rule directly. So how two things in R square map. So this is because this should be linear. These are things of that nature. So this is lambda 1 x1 plus lambda 2 x2 for lambda 1 2 in R. Lambda 1, lambda 2 being real numbers. So this is the space of this kind of functions. To a pair, you give this result where this can be varied. So for different lambdas, you get different functions. Okay. What? Roots. What do you mean by roots? No. I mean just for instance, the function f x1 x2, if it's given by 3 times x1 minus 2 times x2, for example, and therefore f is in, it's a linear function on the plane, and you can vary these coefficients and you get different functions. Okay. Okay, so let's give some remark. This is, yeah, or this is some observation, but so first, as always, consider some R module. Sorry, commutative link with unity, and V be a finite dimensional. If it doesn't have basis or it's infinite dimensional, this will not work. Be a finite dimensional. R module. Then the dimension of V star. We know this is, okay. We know this has dimension. Why? Because it's space of homomorphisms. So this is, so by the previous proposition, this is the dimension of V times the dimension of R. What's the dimension of R? So you have the ring being modulo over itself. What's its dimension? 1. It's like R to the power of 1. So this is V times 1. So this is the dimension of V. Okay. So in some way they are equivalent, but not exactly. They are not canonically isomorphic. So they are, so hence V is isomorphic to V star. However, the isomorphism depends on a basis. So in the previous proposition, when we gave how do homomorphisms correspond to matrices, we fix some basis. E1 to En of V and F1 to Fm of W. So, however, the isomorphism depends on a choice of basis. And so it is not canonical. I'm not going to define this word because we need some category theory. And so we will, so it is useful to distinguish between V and V star. I think so. In physics, they say I think that V are contravariant and V star are covariant, something like that. So yeah, in physics, V. Yeah, of course, if you start with contravariant, the duo will be covariant and so on. And I'll show later that if you take double duo, you get the initial one canonically. So V, they say contravariant, and V star covariant. And so these are like, they're represented by column vectors. Well, if you start with column vectors, in contravariant, this will be covariant with row vectors, or you can start the other way around, but let's fix that. Let's fix some input. And these are row vectors. Here, vectors are in the physical. It's not programming because even in programming, they're just tuples, but in the diagrammatic two-dimensional way of thinking. Okay. So, now, if we choose a basis of V, we can get basis of V star, which is called the dual basis. So let R be a commutative ring with unity, and V be a finite dimensional. So you might observe that sometimes I say finite dimensional, sometimes I don't. When I don't, I mean it's true in general, but sometimes I need to be specific. Finite dimensional R module. And E equals E1. This time it's an order basis. En B, or maybe okay. Let's make it ordered. Doesn't be a basis. No, not ordered. Be a basis of W. Oh, sorry, of V. And then the dual basis is, let's call it E star of V star is given by the functions, the linear maps. So E1, we use upper indices, superscripts, to En. They're linear maps from V to R because these are the elements of V star. They are functions of V2, the base ring. Such that EI of EJ is what? This. So this is the chronicle symbol. Yeah. So this is 0 if E doesn't equal G and 1 if E equals G. Okay. So for example, let's give some. It's interesting to work with non-standard basis, but we don't have time for that. So we are going to do only. Of course, we have to check that this is a basis and so on, but I'm not going to do that. So this is given. This is the basis, the so-called the dual basis. So again, take R squared. So let E1 and E2 be the standard basis of R squared, and then E star, which is the set of E1, E2, is given by the projection maps. So remember I said this a linear function of R squared is just A times x1 A1 times x1 plus A2 x2. And when A1 is 1 and A2 is 0, or the reverse, we get the projection maps. The projection, so E1 of EX x1, x2 is x1, and E2 of x1, x2 equals x2. And it's easy to check that when E1 is applied to 1, 0, we get 1. And when it's applied to 0, 1, we get 0. So we get the chronicle symbol for E1. And similarly for E2. Of course, we can generalize this to any dimension. So the dual basis of the standard basis are the projection maps. Okay. The dual basis. Now let's see how dual bases are useful for working with linear operators in general. Yeah, so to prove that, like, the next, yeah, give some proposition here. And the next, but this is very useful. Because we can work with matrices in single formulas, with operators in single formulas. I will show what I mean. So let R be a commutative ring with unity and take two finite dimensional spaces. So VW are finite dimensional modules. Dimensional R modules. And with, so they have bases. let's go with n. Be a basis. I not say the word order. Basis of v and f equals f1. Sorry. Oh. This should be the next proposition. I just this was what I had initially in mind. Then I thought, okay, I have to give a. So we have only a single one. Is a finite-dimensional R module. Yeah. Take a basis. A is a basis. Of V. Okay. Then and take some vector V. V is vector V. Then V equals sum E from 1 to n EI of V times EI. So E upper, so here of course E star is the dual basis. I forgot to say that. But I will assume when I have a basis that the dual is the dual basis. Okay. You should put this before the statement. So a vector can be determined by this formula. So what this gives? So this gives the components, and for this reason, these are sometimes usually in finite element literature, the dual bases are called degrees of freedom. So okay, let's say that I will say this in words: the components of V in the basis E star, in the basis E, are given by the degrees of freedom I assume you have seen this term in finite element literature, degrees of freedom. And degree of freedom means a dual basis. It took me a lot of time to understand that when I started my PhD, but degree of freedom is just it's a covector. Oh yeah, I forgot to say that. This kind, these are called covectors. The element of V star are called covectors. Maybe you can write it early. So the elements of V are, if they're called vectors, the element of V star are called covectors or one forms. Given by the degrees of freedom applied to it. So applied to. So degrees of freedom, let's say these are E1 to En. Applied to V. Okay. Let's give some, maybe not fully rigorous, but some idea of proof. So let V equals, I would use this terminology for some lambda 1, lambda n in real numbers. This is tensor notation, so we distinguish between upper and lower indices.
Real or elements of the ring?
Okay, yeah, elements of the ring. Elements of the ring. Then, so because this is a basis, it has unique decomposition. So lambda 1, lambda n are unique and exist because it is a basis. And then for E equals 1 to n, we apply the basis EI. EI of V equals, so this is EI of some, let's change the index here to J, lambda J, EJ. And this is, okay, let's write it up. Okay, I'll leave this formula here. So this is, because this is linear, we can put this on that side. So this is some G from 1 to n lambda J times E I of EJ. So because of linearity, we have this thing here. So, but what's this? Delta ij. So this is some G from 1 to n lambda J delta ij. Okay, from this sum, what we have? We have all of them except one is 0. So we only get the index I. You see this thing is non-zero only when I equals j. So then we have delta I lambda y. This is the only non-zero coefficient. Okay, and this is what we wanted to prove. You see, we have this here and this here, and they're equal. So lambda y equals, this concludes the proof. So because the representation is unique, and we get the coefficient from the EY of V. Now I'm not going to write this, but in this trivial case, when maybe give example with non-trivial basis. Yeah, okay. First, I will say in words, if we have this basis, the standard one, and we get some vector xy, then the dual basis will take E1 of xy will be x and E2 of xy will be y. And so here, for example, okay, let's give example. Let's write it down. So V is R squared. And for the trivial case, the standard basis, E1 and is this E2 the standard basis. Equals E1, X1, X2 is given by X1 and E2, X1, X2 is X2. And if we take V equals V1, V2, then this E1 of V times E1 plus E2 of V up V times E down 1 of E2, sorry. Okay. This thing here is the first coordinate. So this is V1 times E1 plus V2 times E2. But let's unpack. So this is V1 1 0 plus V2 0 1, which is V1 V2. So this is fine. Now let's consider more another case. Let's say now take some other basis. So E1 is, I don't know, 1, 2. And E2 is for 1. These are linearly independent, so this is a basis. Okay. Now now we are looking for the up one. So we are looking for, now in general, this will be, the problem will be equivalent to finding an inverse of a matrix, but because it's a two-dimensional, I will write this as a simple high school like system of linear equations. So we are looking for E1, E2 in R squared R, such that E1 of E1 is 1, E1 of E2 is 0. And so this is one system, and then we have E2 of E1 is 0, and E2 of E2 is 1. Okay, so we have two independent systems. So let E1 of X1, X2 equals to I don't know, lambda, I'll just write lower indices, lambda 1 x1 plus lambda 2 x2. Because we are solving linear system, I will stick with down index. Okay. So we have E1 of E1, up 1 of E small 1, equals to lambda 1 times 1 plus lambda 2 times 2, because these are the coordinates. And this should be equal to 1. And E1 of E2 is lambda 1 times 4 plus lambda 2 times 1 equals 0. And so we have this linear system. Let's solve it. So we multiply this by 2 and divide. So okay, I read this. So 1 minus 2 times 0 equals to lambda 1 plus 2 lambda 2 minus 2 times 4 lambda 1 plus lambda 2. And this is, oh, okay, doesn't matter. And this is minus 7 times lambda 1. And so lambda 1 equals minus 1 over 7. Is it right? I think so. And so lambda 2 is minus 4 lambda 1 from the second equation. So this is minus 4/7. And so E1 of x1, x2 equals to plus, yeah, sorry, is minus 1/7 of x1 plus 4/7 of x2. And we have a similar linear system in the other case. So E2 of E2 equals, okay, sorry. So let E2 x1 x2 equals mu1 x1 plus mu2 x2. And then the similar argument, we get the following system. E2 E1 is lambda 1 plus 2 times lambda 2 equals 0. Sorry, this is mu. And E2 is for mu1 plus mu2 equals 1. Again, we subtract the first minus the second twice, so we get 0 minus 1 times 2 equals the same thing, m1 plus 2 m2 minus 2 times 4 m1 2, which is minus 7 mu1. Then so we get minus 2 equals minus 7 mu2, so mu1, so mu1 is 2/7, and mu2 is minus 4 mu1, which is minus 8/7. Again, I could write this as a single problem of finding the inverse of a matrix, but I didn't write this down, so I don't have the theorem for that. That's why I'm using this kind of high school type solution. Okay, so we get that E2 of x1, x2 is 2/7 x1 minus 2 minus 8/7 x2. And now if V is a vector, then V equals E1 times V times the basis vector. So we apply the degree of freedom, and the same E up to V times E2. So we get the following. U1 was this type here. So this is minus 1/7 V1 plus 4/7 V2 times E1 plus 2/7 V1 minus 8/7 V2 times E2. So this is how you decompose this vector in the basis E1, E2. We can check if you want. Do we need to check? Okay. Check. So this thing here, let's call it A. So A is minus 1/7 V1 plus 4/7 V2 times 1, 2 plus 2/7 V1 minus 8/7 V2 for 1. This is E2. So we get minus 1/7 V1 plus 4/7 V2, the first component, and this thing here, plus 2/7 V1 minus, so it plus 8/7, so 2/7 times 4 V1 minus, this should be very big. Did I make any mistakes in the computation before? This will become very, very big. Okay, so 4/7, sorry.
U2 seems to be wrong. One minus, it should be 1 minus 8/7.
Oh, yeah. Because, yeah, it's 1 minus. Yeah. Because I used the previous. Here it was 0, but here is y. Yeah. So this is minus, so this is minus 1/7. Okay. Now it's okay. So we have 2 times 7 times 4 V1 minus 1/7 times 4 V2. And this is the first component. And the second is minus 1/7 V1 plus 4/7 V2. 2 times. This is 2 times, sorry. So times 2 because we have 2 here. And we have 2 times V2. And this is 1 time. So 2/7 V1 minus 1/7 V2. So minus 1/7 V1 plus 8/7 V1 is V1. And 4/7 V2 minus 4/7 V2 gone. Minus 1/7 times 2 is 2 minus 2/7. 2/7. Here in the second component we don't have V1. And we have 8/7 V2 minus 1/7 V2, so it's V2. Okay, this is fine. And now let's make a break.